I will speak about quitting games here. So it's a little bit different. There's no incomplete information, it's something else. So quitting games are repeated games where player has only two actions, namely to continue or to quit. And as long as everybody continues, the game goes on. And as soon as at least one player quits, the game is over and everybody gets a payoff that depends only on who are the quitters. Okay, this is apparently simple game, but it's not so simply, and there are a lot of open questions and difficulties now. What we propose here is to embed this discrete time game in a continuous time setting, because this permits us to handle some particular pathologies of these games and to treat them with tools of analysis, for instance. Okay, so this is a common work with Khaled Ashkenazi, who is currently in LSE in London, Ilya Krasikov, who is between Moscow and somewhere else in the world where it is better to live now, and Alon Solan from Tel Aviv. Yes. Okay, the outline is the following. So I will start by defining quitting games and to explain two important examples. Then I will present the continuous framework. The main tool is what we will call the absorption process. And at the end, I will show you different applications. Okay. So of course, don't hesitate to interrupt me, to ask questions or to make remarks or everything else. Okay, what is a quitting game? So as I said, a quitting game, so it's defined by a couple. There's only a couple. I is a set of players, it's a finite set. Then when we say that it's a quitting game, we know already that each player has only two possible actions, namely quit, here, this is a Q, and continues, that is a C. Okay, so we don't precise this in the definition of the game. As input, as usually, we write A for an action profile, and capital A is a set of all action profile, and we have a particular action profile, namely the vector C, where everybody continue, and we denote by A star a set of the action profiles where at least one player stops. Okay, and what we need to define else is the payoff. So to each action profile, we associate a real number that corresponds, a vector that corresponds to the payoffs of the player. Okay, and how the game is going on. At each step, so it's a discrete time game, at each step N, each player chooses an action between quitting or continuing. And if all players say continue, I continue, then everybody goes to the next step. And if at least one player says that he stops, then each player gets Ri of An, and then the game is over. And if nobody ever stops, at the end, every player I gets Ri of vector C. Okay, is this clear? So in other words, more formally, if we have a sequence of action profiles, we can define theta as the first moment where at least one player stops, with denoting with setting the infimum of the empty set is infinite, And the payoff is R of A theta if theta is finite and R of vector C if it's infinite. Okay, so then next, of course, this game only makes sense if players are also allowed to play randomly. So since the player have only two possibilities to quit or to continue, at each step, the action of the player is determined only by a real number between 0 and 1, and we can define a behavior strategy for player I as a sequence of numbers between 0 and 1, which says that if but the interpretation is the following, that if xin is the probability that the player I stops at stage n, given that the game hasn't stopped before. Okay. And if we put all these behavior strategies together, we get the strategy profile. And as usual, this strategy profile induces a probability on the set of actions. And the payoff of the game can be written here as before. If theta is the first time where somebody stops, we get R of A theta. And if nobody stops, we get R of vector C. And since now this theta is random, we take the expectation and we call this gamma of x. This is the game. The definition of an epsilon equilibrium is standard, namely for all epsilon, we call epsilon equilibrium a strategy profile where nobody gains by defeat, more than epsilon by defeating. Okay, this is the same as usual.
I have a question. Hello. Yeah. So how is a quitting game different from a stopping game? I mean,
a stopping game. In a stopping game, you have a payoff that depends on it depends on time, and yes, it's simpler than a stopping game usually. Yes, the payoff of in particular in stopping games, the payoff depends also on time where you stop. And here, what is interesting is that times not matter at all.
So there is no state here as such, right? This is what you mean by time. Okay, yeah.
Yes.
Okay, thank you.
In particular, it is not discounted. It's an undiscounted game.
Okay.
And the fact that it is undiscounted brings a lot of problems.
Thanks.
Thank you for the question. Okay, a proposition, what is known about these games? We know since a long time that every 2 and 3 player quitting game admits an epsilon equilibrium for all epsilon. Okay, in general, the question about epsilon equilibria is still open, but we have the following, namely, if there is an epsilon equilibrium for every epsilon, then it has to be from one of the 3 following times, namely, or for epsilon small, we have an epsilon equilibrium where some player quits with probability 1 at the first stage, and then if you don't stop, everybody punish him immediately. The other one is the other possibility is we have equilibria that are stationary. This means that here in the behavior strategies is probabilities that don't depend on time. And the third possibility is that for all epsilon small, there is a strategy profile where the player are sequentially epsilon perfect at X, where sequentially epsilon perfect is also the usual definition. This means that, so there are only three possibilities, and the first and the second one are quite easy to check. And so this permits really to focus on this third possibility, namely to look on sequentially epsilon perfect equilibrium. Here is the first example. So this is a famous example, namely we have a three-player game. You can read this tabula in the following way. The first player plays the lines, the second player the columns, and the third player plays the block. So for instance, if first player quit and the two other continues, we are here and here and here, and first player gets 0, second one 2, third -1. What is particular here, you can see that if nobody, so the payoffs are between -1 and 2, the worst is -1. When everybody continues always, everybody gets -1 here. And if everybody continues, this is here, here, and here, everybody gets also -1. So nobody would like never to quit, and nobody wants that people are quitting together. And what is also to be mentioned is that there's some symmetry between the two players, of course, and there's some red 0, and it is red because it will change after. Okay, so it is known that this game has a 0 equilibrium. Here's the formal definition of the 0 equilibrium. This is an explanation in a tabula. So what is the 0 equilibrium? The first step when n is equal to n, the first player quits with probability 1/2, the other ones continue. In the second step, if the first player has not quit, so with probability 1/2 also, the second player will quit with probability 1/2, the other one continues. Then it's the turn to the third player, and again we start again with the first player, and so on. Okay, and what you can see, or what you can compute is that the associated payoff is 0, 1, and 0. Okay. Remark. So it is easy to compute this payoff. It is easy to show that it's an equilibrium. In particular, let us see what happens if the player 3 quits at stage 1. If he deviates and quits here, then the game is over at the first step with probability 1. And with probability 1/2 here, there are two players. There are two quitters, Q1, player 1 and player 3. So we are here, and the third player gets 0. And with probability 1/2, the player 3 quits alone. And then we are here, and here, and here, and he gets 0. And so the payoff of player 3 will also be 0. And so he has no reason to deviate. Okay. This is a simple game. Now let's change a little bit. Now the red 0 is changed in a red eta with eta small. What happens now? What happens now is that there's no 0 equilibrium. What we can see. So for instance, if you look on the strategy profile before this one, 1/2, 1/2, 1/2, 1/2, the associated payoff is still the same. Why? Because in this strategy only affects the action profiles where only one player is quitting here and here and here. And so it does not depend on the red numbers. And so we have, as before, the associated payoff that is 0, 1, and 0. Okay. And now, if we look on what happens if player 3 deviates, then the new payoff is what? It is the same computation. Here, again, with the game stop at the first stage, with probability 1/2, there are the 2 quitters. Here, the third player gets eta. And with probability 1/2, there's a lone, he quits alone, and he gets 0. Okay, so these are small computations that shows that in this case, the third player gets eta over 2, that is strictly positive. So it is not x before, as before, it's not an 0 equilibrium, because player 3 profits by deviating. But if epsilon is greater than eta over 2, it is still an epsilon equilibrium. And what happens? Here's interesting thing. Namely, what can be shown is that for all epsilon, we can find an epsilon equilibrium. How we do this? We take M large, and you choose rho such that 1 minus rho to the power of M is equal 1/2. And then once M and rho is fixed, we will do this following, namely at the first step, the first player quits with probability rho. If he hasn't quit here, what happens with probability 1 minus rho? He quits again at the next step with probability rho, and so on, while the other 2 players do nothing. And at the end, if the game hasn't stopped at this stage, namely with probability 1 minus rho times 1 minus rho times 1 minus rho, so with probability 1/2, then it is returned to the second player. Do the same thing, and then it is returned to the third player, and so on and so on. Okay. What happens here? The payoff will be the same. Why? Because at the end, the first player stopped with probability 1/2, and then the second with probability 1/2, and so on. And so it is the same payoff at the end, because the game is not discounted. But what happens if, for instance, the third player deviates? In this case, if he deviates at the first step, he gets again 0 with probability 1 minus rho, and she gets rho times eta here, rho eta with probability rho. This is eta times rho, which is smaller than epsilon for large M. Okay, what does this mean? What is the sense of this? This means that the first player wants to quit with probability 1/2, and he doesn't want that third player quit. And to avoid or to minimize the influence of quitting of the third player, what does she do? She will decompose her quitting, her 0.25 probability of quitting, in a lot of small probability, such that if somebody quits with her, the probabilities that it happens will be very small, and so it won't impact a lot the payoff. Okay, and so smaller is the probability that the first player quit, and so smaller is also the payoff and the loss that she gets when some other quits with her. Okay. So what happens now? So of course, this works with all epsilon for small epsilon as small as we want, but not for 0. And what happens if we tend epsilon to 0 or m to infinity or rho to 0? If m tends to infinity, then we have to tend rho to 0. And in this case, if you use the usual topology of the sequence in Rn, the strategy converges to a degenerate strategy where everybody stops with probability 0. This means at the end, on this limit strategy, the associated payoff is the payoff where nobody stops, and it is -1, -1, -1. So firstly, we see that the payoff is not continuous in the strategies, and also that the limit strategy is not a zero equilibrium. Okay. And what we will do now is to change a little bit the setting in order to get a non-degenerate limit and also to get the zero equilibrium. And the first idea to do this is to change the time scale. Okay. Why? Because here the natural time scale is n, is first step, second step, and so on. And when epsilon is 0, we have to take more and more time to develop our strategies. But what happens, even if m becomes large and rho small, the probability at the end of the first run of the first player remains 1/2, and the second run remains 1/2, and so on. And so what we propose firstly is to change time and to take the time, the probability of absorption. Here, this will be the definition of the absorption. So what we will do is, so first of all, we focus on strategy profiles where theta is finite with probability 1. We could see that X is absorbing. And this means that the game is over with an infinite time. This is just a restriction. It's not very important because else we can also modify a little bit, but it's not so interesting. And what we do here, so first of all, we set T0 is equal to 0. And for all n, we set Tn as a probability induced by the strategy profile, set theta n is smaller than n. And here, oops, I have my pictures. Here, picture. So look, here the picture is the following. For our first strategy profile, T0 is 0, and then T1, the probability is that theta, the game stops before the first in the zeros, in the first step is 1/2, so T1 is 1/2, T2 is 3/4, this plus this times 1/3, and so on. T3 is 7/8, and so on and so on. Okay, what we do next is that we define, I think I will stop switching, is to describe, so we have now the time scale, and then we will associate to the strategy profile a map. This map goes from the probability time scale and the action profiles which are stopping to 0, 1, and for all t and all a, pxt of a is the probability not only that theta is smaller than n, but also that the stopping is made, the quitting is given by the strategy, the action profile A. And to get a path on continuous time, we define this path from Tn-1 and Tn. Okay, so here, the picture that corresponds here. So we have now our time. This was our time scale. And then, for instance, for the action profile where the first player is quitting, he jumps immediately from 0 to 1/2. So between T0 and T1, it is the only quitter. So it is a probability that theta smaller than n here. And then after this, nothing happens, so it remains constant. And then again, check the probability that he is a quitter, augment a little bit, and so on and so on. And we have the corresponding picture for the two other non-zero absorption paths where the second player is a quitter. So between the zeros and the first step, nothing happens. The second player does not quit, and then he quits with probability 1/4 and 1/2 times 1/2. And then it continues, and then it is the turn of the third quitter, and so on. Okay. An important tool here is p-hat, that is a sum of all this, that resumes the quitting of the game. Here, if you have here this picture, if we take the sum of all this, here we recover T1, here it is T2, and so on, because it's simply the probability that theta is smaller than n, and we complete it to a path for a function on 0, 1. Okay. So this is a picture that is associated in the graph, and the function pi that it associates to this first strategy profile. Okay, we see that to all strategy profile you can associate a function pi. Let's look what this gives for the second one. For the second one, it's a little bit more complicated. Here, you see that the first player will immediately quit with probability rho, then his probability of quitting goes from rho to rho plus rho square, and so on, and so on, and so on, and so on. And then when it reaches 1/2, one half, it is a turn of the second player, who here jumps to 1/2 times theta, and so on and so on, and that is the turn of the third player, and so on. And if you look on the p-hat here, the size of the shape of the p-hat is a little bit different. There are more jumps, and it is closer to the diagonal. And here, if you look at the limit, so here you have maps, and if you look at the limit of these maps, for instance, in the weak topology, when rho tends to 0, you get the following. You don't get something that is degenerated, but simply the following. Namely, here, a period between 0 and 1/2 where the first player quits infinitesimally, but in very frequently, then until it reaches a probability of 1/2, and then it is a turn of the second player, and then it is a turn of the third player, and the sum of these probabilities of quitting will be t at each time. Okay, let us go back to the definition. Okay, so if you look on this definition associated to the special strategies profiles that we get before, what we can think is that if you're here, you can also imagine something more general. Namely, we can define an arbitrary absorption path where you can mix what happens in the discrete-time case and you mix with what happens in the limit case, and you can have something where it jumps immediately. So it is a discrete strategy. Here in the second step it jumps also. Then somebody quits continuously. We can have accumulation points of jumps and then continuous and so on and so on. Okay, this means that we can alternate periods where we have discrete time jumps here, and continuous time quitting, that is here and here. Let us, if you look on more formally, what will be a general absorption path? We have to, this absorption path will be mapped. So from 0, 1 times the quitting action profiles to 0, 1. They are always Cadillac, they are non-decreasing. And if you define the sum of all bits of A, the sum of the A and the jumps, you can separate. You have two sets which are interesting. The set where we have T's equal to, is equal to T, where the game plays continuously, and the set S, where we are in a discrete strategy. And what we need to be really an absorption path is firstly that the B head of T is greater than T, as in the examples we have shown before. That between the sets T and S and connected components between in 0, 1 minus T union S, pi is constant. Okay. This is the shape what we saw before. Then a third thing that we need is if there's a jump, then it must come from an action profile, a quitting action profile of the real game, namely the jump, given that the game has to divide it by I1 minus T, so divided by the probability that the game is still going on at time T, has to be the jump, the probability that the game is over, that derives from a real action profile, the strategy profile. Okay. And then the last thing is what we said before about the rule strategy, is that the fact that we divide the probability of quitting in very, very small probability makes that it is not interesting and not possible for the other player to quit also. So when there's a continuous quitting period, there's only one player who is quitting. So in other words, the derivative of Pt of A is 0 for all T in the continuous time period, except for one player, or except for the game of no, sorry, I don't know what. My phone is happening. Okay, yes, now it's okay. Okay. So interpretation. What is this interpretation of this absorption path? So Pt of A is the probability that the place is absorbed by some A until the total absorption probability is T. And all T on the jump points correspond to plane discrete time. And all time T in the continuous period correspond to a plane in continuous time. Okay. And what we have here, and what is the main, what is important here, and what we wanted is, if you look on the set of these absorption paths with the 4 properties that we, I don't know how to, it's an old telephone, I don't know how to, I think I will, okay. Firstly, it contains all absorption paths that are derived from a usual strategy profile, classical profile, strategy profile. Secondly, if you have for every arbitrary element of A, this element is the limit of a sequence of real strategy profile of the absorption path derived from ordinary strategy profiles, and the set A is compact. Okay, and this permits us to pass to the limit and to get 0 equilibrium. For this, we have to define payoff path. What is the payoff associated to the absorption passes? It is for all, so it's a map from time to the elements of Ry. For all t, we can, the payoff associated at time t to the payoff absorption path pi is the sum of the payoffs for the action profile A times the probability after time t that the absorption has been done by this action profile t, divided by the probability that the game has not been finished before. Okay, the remarks are the following. Gamma of t is of pi is the expected payoff after absorption probability t. And after the time, after that p hat of t is equal to 1, you can define everything you want because the game is over at this time. So we can set 0 or anything else. Okay, and of course, what we need is that if the absorption path is derived from a usual classical strategy profile, then the payoff at time t n minus and the payoff associated to x after time n coincide, of course. So again, there is a correspondence between the payoffs of the classical strategy profiles and the payoff absorption paths. Okay. What is sequentially perfectness here? There are 2 things to see. So we don't have a compact one point definition. It is if t is in S, the definition of, so for all t in S, for all t we have a condition. If t is in S, the player I is epsilon sequentially perfect if it's epsilon perfect on the action profile for the one-shot game with payoff with a continuing payoff. This is the usual definition that is also valid for discrete-time games. And in the continuous time, and when the t is in continuous time period, then what do we need? We need that if at this time t, a player is quitting, then he does not gain more than epsilon over what he would gain if he continues. And if the player is a quitter or is a quitter, then modulo epsilon, he is indifferent. Okay, so again, this is adaptation, the usual adaptation to sequential epsilon perfectness. And we say that an absorption path is sequentially epsilon perfect if all players are sequentially epsilon perfect. Okay, and the theorem is what we wanted. What says the theorem, namely for all epsilon small, if there are no trivial cases, namely the trivial cases where the game terminates with probability 1 at the first stage, or the other trivial case where the player always continues, this is epsilon continues. If there's no such equilibria, then, and if for all epsilon there's an epsilon equilibrium, the standard game, then if and only if there's a then there's a zero perfect absorption path. And if there's a sequentially zero perfect absorption path, then it corresponds to a sequence of epsilon equilibria in the standard game. Okay. Some applications. So what we are in particular interested in are the absorption paths which are continuous. This means that there's no sums. So in particular, in this case, in the case limit case that we had before, here this is a continuous case. Here, as I said, T, where player plays in continuous time, is 0, 1. Okay. And what is interesting in this case, what is particular, is that if, okay, no, but we do here is to say, we have two applications. The first application in this case is that we can find a sufficient, as what we have here is that the payoff of this absorption path is only determined by the matrix Ri of QG C minus G. This is the matrix of what gets the player I when the player Q is G the quitter. Okay, we get the sufficient condition on this R gamma for the existence of equilibrium. And the tools here are linear complementary problems and viability. Okay. And the second application is an algorithm, is to show an algorithm, to build an algorithm on graphs, on the graphs on quitters. So we can build a directed graph on the quitters to compute continuous absorption paths which are equilibrium. So what about this linear complementary problem? So as we always already said, is we focus on games on absorption paths which are continuous. Then, as we said, we can focus on the matrix Ri of QG C minus G, namely the payoffs of all players when only one player quits, because these are the only payoff that matters. We suppose a normalization that says that if you quit, then you get 0. This is the case for the example we had before. And we can define the following linear complementary problem. This was introduced by Kottel and Murty, for instance, in the 1980s. And it says the following. If you fix the matrix R and the vector Q, then the linear complementary problem, LCP of R and Q, is the following problem. Namely, you have to find a vector V, W, and the probability Z on 0 until n, such that we have the following relation. What does this relation mean? So that W is, yeah, what does this relation mean? The interpretation here is the following. suppose that Q for some T in our absorption path, Q is a continuous payoff, the gamma T of P. And Zi, Z1 over Z0 is the probability that the player, everybody continues. This is the probability Z1 that player 1 quits, or until Zn that player n quits alone. And what gets the players with this probability at the end? They get the probability that everybody continues times the continual payoff plus the payoffs where the ith player quits times the probability that he quits. Okay? And what we need to find, so we need that this, what we are looking for are sequentially perfect absorption paths. So we want that it is non-negative, so it is always better, or at least indifferent to continuous. And if you are the quitter, so if the probability that you quit is positive, then you have to be an indifferent. So this linear complementary problem that originally is used for operation results is tailor-made for problems of sequentially perfectness. And what we have here is the theorem that says, well, I can switch to full screen, is that suppose that for a given absorption path, no, suppose that for a quitting game, the matrix R of gamma and all its principal minors admit, and all Q and Rn admit a solution for the LCP problem, then in this case, the gamma admits a continuous sequentially zero perfect absorption path. Okay? So the idea behind is to say that the payoff function and its probabilities has to belong to a set that is defined by this LCP problem. And by the way, they are defined through a differential equation that come directly from the fact that we have a continuous time, we have a continuous absorption path, and we find finally a problem of control, a viability problem, okay, that we can solve with arguments of viability. Okay, and what about the algorithm? What we can, again, if we look on a continuous absorption path, we can define a map I, iota, such that for all t, iota t is the quitter at time t. Okay, so recall that if you have a continuous absorption path, at each time there's only one player who quits in continuous time, and you can define the continuous absorption path just by the function iota of t. Okay. Then with this iota of t, you can build a directed graph. The edges are the corner are the player here, and the edges are, we put an edge between I and G if we have the following relation between the payoff. Namely, that if I is the quitter, the payoff of the second player of the G player is smaller than 0, and the payoff of the ith player, if the G's player is the quitter, is positive. And what we have is this relation determines exactly the sequence of the players in a sequentially perfect equilibrium. Okay, so absorption path pi is a sequentially perfect equilibrium if the sequence of the quitters are exactly in the graph. Okay, and what we are doing now, and what we are already almost finished, is that we can define conditions on the graph, on this graph, to determine the existence of continuous sequentially equilibrium, and we can also describe an algorithm for finding all continuous equilibrium of some contingent. Okay, and we can, what we have already done, this is almost finished. We have a lot of examples where we can calculate. If you look on this example, if you see here, so here's the example, the first example, the second example where we have tend rho to 0 and m to infinity, and where the first player quit with probability continuously with probability 1/2, and then the second player with probability 1/4, and so on and so on. Here's the iota is equal to 1. So we know already that it is sequentially perfect equilibrium. Here iota t is 1 here, then iota t is 2, iota t is 3, 1, 2, 3, and so on. And so the graph that we have here is the graph that goes from 1 to 2, to 2 to 3, to 3 to 1. So it's a simple graph that is circular here. And we find an equilibrium with the algorithm that I want to detail here. Okay, thank you.